Normally, systems consist of a number of subsystems which are connected to each other in a given configuration. RAM modeling is used to find the reliability and availability of the overall system from the RAM parameters of the constituent subsystems. This is achieved by developing a graphical or mathematical model of the system. Generally, two methods are employed for RAM modeling, which are reliability block diagram and Markov chain analysis. Reliability block diagram is a technique to find the reliability of the overall system from that of its constituent units. The system is modeled into a number of blocks with the given reliability, and these are normally connected in series, parallel, or a composition of series parallel configuration. As reliability is an inherent property of the system, repair time is not considered for calculation of reliability. Generally, Markov chain analysis is employed for computation of availability of repairable system. Markov chain analysis is used to derive reliability and availability of a system from the RAM parameters of its constituent units. The system is modeled into a number of states with known probability of state transitions. Reliability and availability of the system are derived from this state diagram. It is important to note that Markov chain analysis considers the failure time as well as repair time of the system, in addition to the time for which the system functions normally. Therefore, the reliability as well as availability of the system can be derived by this technique. We will now explain the concept of reliability block diagram, or RBD in short, with the help of an example of a railway communication system. In this system, a communication switch is provided in the control center as well as in each of the stations. The communication switches are all connected in a daisy chain configuration. It can be seen in the diagram that all switches must be working for the communication system to function. If there is a failure of a switch at any station, there will be a communication failure at that station as well as at all stations beyond that point. For example, if there is a failure in switch 2-1 at station 2, the communication will not be available at station 2 and 3. This is considered as failure of the communication system. Reliability block diagram of the communication system is shown in the figure. Here each block represents the reliability of the corresponding switch for a given time t, or in other words, probability of survival of the switch for a given time t. As all the switches must be working for the communication to be available, all these blocks are put in series. This is called a series system. One important point to note in computation of reliability through RBD is that the reliability represented by each block should be independent of all other blocks. This means there should be no common cause failures between the blocks. A good example of a common cause failure is use of common power supply for the subsystems. If there is any common cause failure, the RBD must be modified suitably. In the present case, if reliability of the blocks are R1, R2, R3, and R4 respectively, the overall reliability of the system will be R1 into R2 into R3 into R4. Now let us consider the railway communication system discussed earlier. To improve the reliability of the communication system, a ring architecture is employed. In this architecture, one additional communication switch is provided at each station, and these switches are connected by an alternate communication medium. Provision of two paths of communication ensures that failure in one path will not cause a communication failure. Let us consider the failure that we discussed earlier, that is, failure of switch 2-1 at station 2. This failure causes one communication path to be unavailable. However, communication will be available through the lower path of the communication system as shown in the figure. The resulting reliability block diagram for this architecture is shown in the figure. This is an example of a series parallel combination where sets of blocks in series are placed in parallel. In the RBD, each arm represents one path of the communication system. Assuming that each block of the RBD is independent, that is, there are no common cause failures between the blocks, and also assuming for simplicity that reliability of each block is R, the reliability of each arm will be R to the power 4. The overall reliability of the RBD or the communication system can be calculated by probability theory, and this will be as shown in the expression. The figure on the screen shows the ring architecture that we discussed earlier. We also saw that this architecture can tolerate failures in one of the communication paths as shown in the figure. Now suppose a second failure takes place in the alternate path of communication. Say switch 02 of the control center fails as well. In this situation, communication will not be available at stations 2 and 3. To deal with such situations of multiple failures, links are provided between the switches of a station at selected stations. The link provides communication between the two paths. Let us see how this link helps in dealing with multiple failures. Due to provision of the links, it is now possible to tolerate some multiple failures in different paths of communication. In the present case of multiple failures, the link ensures that communication is available as shown by the green arrows in the diagram. The resulting reliability block diagram is shown in the figure. It can be seen that due to provision of the link, RBD has become complex and it is not possible to solve it by simple series parallel combinations. In this case, the method of decomposition of RBD is employed.